Hi there, welcome to a new day, welcome to a new lecture, lecture 4 in the quantum field theory course. Today is an exciting lecture. We get to look at this recipe, this canonical quantization recipe to actually quantize one of our field theories. So we're going to have we're finally going to meet a quantum field theory in this lecture. I just want to review some of the things we've done before we head into new territory though. So just to give you a recap of the big picture. So we've been considering the classical theory of a very particular theory, of the theory of a real scalar field. So we can define this theory with the following Lagrangian, or technically Lagrange density. So this is the Lagrange density for a free scalar field. And when you apply the machinery of the Euler-Lagrange equations, you end up with the Klein-Gordon equation, which is shown here. So this is the field, the classical field equation that phi must obey. And then we did a little bit of analysis on this equation. So one thing we saw that was when you go into momentum space, so whenever I look at my solutions not as functions of x, but as functions of momentum, of momentum k, that each mode, so each mode described by this label k, this momentum label, behaves as a simple harmonic oscillator. So this real scalar field has this link to an infinite number of uncoupled oscillators, okay, where each oscillator is the momentum k mode. So motivated by that, thinking about the fact that we're seeing oscillators appearing from the Klein-Gordon equation, we reviewed some of the material for how to quantize the simple harmonic oscillator in quantum mechanics. And in particular, we reviewed this formalism where you use these creation and annihilation operators. So the creation operators are A Dagger. And here we have states labeled by n, by the number of, well, we're going to think about it as the number of particles in this state. So what the creation operator does is it gives me a new state that has a number which is higher by 1. And the annihilation operator reduces the number. So it goes from a state n to a state n minus 1. I've just put in the proportionality signs here because I haven't written down the correct normalization. And I didn't want to get into the details. Okay. So in the lecture yesterday, we wrote the operators A and A Dagger in terms of x and p. But it's trivial with a little bit of algebra, to invert the relationship. So here's the inverted relation. So it turns out I can write x, my position operator, in terms of A and A Dagger. And I can write p, the momentum operator, in terms of A and A Dagger. And also the Hamiltonian for the system. So this is something we did look at. So the Hamiltonian is simply omega times A Dagger A, and then there's this factor of a half, which is the so-called 0-point energy. And of course, these are quantum objects. Quantum objects obey commutation relations. So there are commutation relations that A and A Dagger obey. So A Dagger gives me the identity. And then there's some defining relations here with A and A Dagger on the Hamiltonian. So these are relations that we'll use later in this lecture. Okay, so that's a brief recap. We'll next go on and we will consider some new things. Okay, so on to new things, and the first thing I want to begin with is a rather trivial generalization. So we said the Klein-Gordon equation is related to an infinite number of oscillators. We have reviewed what happens with one oscillator. Let's just spend a few minutes generalizing it to the case when we have multiple simple harmonic oscillators, because this is the case that's really going to be relevant for our scalar field theory. So it's pretty easy to generalize the theory from 1 to n. And remember, we're always looking at uncoupled oscillators. They all act independently of each other. So the total Hamiltonian for n uncoupled oscillators, well, we can write it as the sum of the Hamiltonian for each individual operator, or each individual oscillator, and because each oscillator is independent, it just has its own Hamiltonian, which we can just label by k. So this is reasonably straightforward. Okay, we've just written down the sum of n uncoupled Hamiltonians. So now we could go through the same story and we can introduce creation and annihilation operators. Call it tiger for the creation and the annihilation operators. And now we just put a subscript k on it to indicate that these creation and annihilation operators only act on the kth oscillator. Okay, so what this means in practice then, if I act some state with my k raising operator, let's act on a state which I can label all with the occupation number of each of the individual uncoupled oscillators. I'll go n1, n2, I'll have an nk, I guess I'll go all the way up to nn. There's n uncoupled oscillators. So what this creation operator does is it'll increase the occupation number for the k case. It'll go from nk to nk plus 1. So that's trivial, okay? And the annihilation operator would do something similar. So there would be a kth annihilation operator. And of course, these things are quantum objects. They're going to satisfy certain anti-commutation relations then. So it's a trivial generalization of what we've looked at before. So we again have that the annihilation operators, the commutator, even when k and q are different, are going to be 0. So they commute. And that's also going to be true for our raising operator. But when we look at the commutator for a mixed, so we've got AK, a dagger Q, okay, this is going to be delta KQ. Okay, so if K is Q, we get 1. If K is not Q, we get 0. Okay, trivial. And obviously it agrees with what we had before. We set K equal to Q, we get back 1, which is what we had for the single case. Okay, so again, we can define states in this theory. We can construct states. So we can start with the vacuum. The vacuum state in this case is the state where when we act on the state with a annihilation operator, we get 0 back. And to be in the true vacuum state, this must be true for all k annihilation operators. And then we can build up all states from the vacuum if we want. So we can construct, say, the state n1, n2, nn by acting on the vacuum with these creation operators. So a1, we act n times. A2, we'll act n2 times. And so on. Okay, and let's put into the normalization so that these things are normalized to unity. We have n1 factorial, n2 factorial, all the way up to n factorial, and this has to act on the vacuum state. Okay, so by acting on the vacuum state with these creation operators, we can build up any state we want. So there's kind of technical names for this. This is the so-called the occupation number representation, because we can completely specify the state by the occupation number of the kth n value. Okay? So I guess I can give you an example of the types of things we can look at. So we could, if we have a state labeled by n1 to nn, we could act on this with the total Hamiltonian operator. So from our definition of the total Hamiltonian, set as the sum of Hamiltonians for uncoupled oscillators acting on the state. And this will just return the eigenvalues E1 plus E2 plus up to En times the state. And here, each of these E's, it's called Ek, is simply omega nk plus a half. Okay, so E1 is omega n1 plus a half, so whatever n1 is, and so on. So we can just by specifying the numbers, we're able to determine what the total energy is for this state. Okay, so that's the generalization then to from one oscillator to n oscillators. Okay, so as I said, fairly straightforward. Next, we'll go on and discuss something which is less straightforward. Okay, so next I want to discuss the procedure we can use to quantize a theory. So to go from a classical theory to the quantum theory. So this is the procedure we're going to use is called canonical quantization. There are different ways to quantize theories, but we're going to just look at this one called the canonical quantization procedure. I think I've spelled correctly. Okay, so this is the way we're going to use it. We're going to use it like a recipe to go from a classical theory to the quantum theory. Nice things about recipes is, you just have to read it, reproduce the steps, and you end up with something nice at the end, hopefully. Some of the steps can be complicated, depending on the recipe book you're using, and that's going to be true here as well. Sometimes it'll be easy, sometimes it'll be hard. We're going to try and stick to the easy case. But in principle, it works for much harder things as well. Let's go through the recipe. So 5-step plan for quantizing a theory. Okay, so plan 1.1 is we start by writing down what the theory is. The way we can write down what the theory is to write down a Lagrangian. So this is to some extent where you have the most degree of freedom whenever we're using this procedure, because the Lagrangian could be very general. I mean, in practice, for most theories in particle physics, we restrict them heavily by ensuring that they're consistent with the Lorentz invariance, and in QED and so on, we insisted they're consistent with all of these gauge symmetries and all of this extra stuff that we can impose on the theories. But in principle, we have a lot of freedom to begin with in step 1. Okay, so we start with our Lagrangian. Step 2 then is to calculate things that we already know how to calculate. So we want to first of all calculate this conjugate momentum. Just differentiate the Lagrangian with respect to the time derivative. And the canonical quantization procedure uses the Hamiltonian. So we also want to work out what H is. This is a function of these two fields, phi and pi. So far, we can do all of this. Step 3 then, where we meet new things. So we want to treat the fields, so these pi and phi fields, as operators. Okay, so this is where it's starting to become more quantum mechanical. So we're now going to treat them as operators. And just like in familiar quantum mechanics, our operators obey commutation relations. So we're also going to impose commutation relations on our field operators. To impose commutation relations. Okay, so far so good. So step 4. So we have these fields which are not operators, and they're going to obey commutation relations. The next thing we want to do is to expand our fields in terms of of these correlation and annihilation operators that we've just been considering. I've been trying to motivate why this may be sensible by looking at the Klein-Gordon equation in momentum space to see that there should be a link with simple harmonic oscillators, but in general we want to expand these fields in terms of correlation and annihilation operators. And this is fine, we have operators, so we're going to be expanding operators in terms of other operators. And then there's a fifth step that we might not get onto in this lecture, but certainly it's going to be an important point and we'll discuss it. So point 5 is to apply what's called normal ordering. So I'll just put this in brackets because I suspect we won't get into it on this lecture. We might hopefully see it in the next lecture though. Okay, so 5 steps. Easy peasy, you just have to follow them. So we know of a Lagrangian that we've been looking at. We've been looking at the real scalar field. So why don't we apply this recipe to this theory that we've been considering. And hopefully we'll end up with a quantum theory at the end of it. Okay, so step 1 was to write down the Lagrangian. So let's just do that. Done it many times now, so it should be familiar to you. Step 2 was to calculate the conjugate momentum and the Hamiltonian. So we should know how to do this now for this theory. So serves pi is phi dot, and our Hamiltonian density is a half I squared, a half the spatial derivative of the field squared, and a half m squared phi squared. Step 3, we want to promote our fields. So we have these pi and phi fields. We want to promote them to operator. So let's do that in a very simple way by rewriting them, but with hats on top. Voila, we now have fields. Okay. Okay, so we've not indicated that we're going to, everywhere we had the field, we're not going to replace it with this operator value thing, and we're going to indicate it with a hat. The more non-trivial thing was we have to define commutation relations. So let's write down what these commutation relations should be. So these commutations, or commutators, are going to be valid at equal times. So let's see where time enters into it. So the most non-trivial one, we have the field phi, commutator with the momentum conjugate pi. So we're going to consider it at a different space-time position, so y instead of x, but they're equal time commutators, so at the same time. So t is the same in both cases. Okay, and this is going to be I. So now that these are continuum fields, we're going to have that they're give a delta function times I as the commutator. So this is supposed to remind you of a familiar one from quantum mechanics. xp is, well, let's do it. xipj is I delta ij. Okay, so we have the factor of I, and we have something that's similar to ij. Okay, we have this delta function, delta xy, in the case of the fields, but structurally it looks similar to the familiar relation. And then the other two we can look at are the commutators of the fields with themselves. Arrows to indicate their vectors. So this commutator is 0. Again, just as x in quantum mechanics, x with x was 0. And our conjugate momentum, again, going to end up being 0. Oops. Going to end up being 0 in the same way that the momentum operators in quantum mechanics also have a commutator that's 0. So good. So this is the step 3 done then. In this theory, it's relatively straightforward because we have a single scalar field, a single scalar momentum. So these are all of the commutation relations we need. As I said, the only thing is that they're defined at equal times. Not too hard to implement. Okay, let's go back up. Step 4 was to expand the fields in terms of creation and annihilation operators. Let's talk about how we do that. So let's remind you of what we had for the simple harmonic oscillator, the 1D oscillator. There we were able to show that the position operator can be expanded in terms of creation and annihilation operators. It was A plus A dagger with some normalization factors. And let's remind you what the classical expansion of the Klein-Gordon solution looked like. Gordon solution. So we looked at this before. It was phi x. We had a d3k over 2 pi cubed. And then I put in this factor of root 2 omega k. Okay. There's 2 omega k's appearing in both cases. And then we said that this is classical, remember? So these A numbers that I'm about to write one of them, is just a classical amplitude. I'm working in, well, I haven't put the time sentence in here. So these are the 3 vectors, E, I, K dot X. So this was the initial Fourier decomposition that we're using. I guess I should put that as a star because it's not an operator, it's just a complex number. So remember, we needed this term and the second term to ensure that our field was real. And or let me remind you what omega k was. So we said omega k positive square root a squared plus m squared. So in analogy with these results, let's talk about what we're going to do with our quantum field, or rather our operator field. So we're going to write it as an operator, a little hat on it. And again, let's do it as we let's do something similar to here. So we're going to consider it as a function of x. So we'll come back to the time dependence in a second. We're going to use the same normalization factors. Okay. And the difference, so we're now expanding this solution in terms of creation and annihilation operators. So we're going to actually have these being operators. So we have an annihilation operator for the kth mode plus a creation operator. And we're doing this, remember, because we said that each momentum mode of the Klein-Gordon equation behaves like an independent simple harmonic oscillator. So we're using these analogies that we have, both of the position operator. So the field is the thing that's analogous. When you go from quantum mechanics to field theory, the field is kind of analogous to position. So structure similar. And then when we go from the classical solution to the quantum solution, we replace what were previously numbers with operators. Okay, so that's first 4 steps. Step 5, we'll return to. The normal ordering step we'll come back to consider in a second. Okay, so let me pause for 1 second there. So reached a nice point. We've expanded our field in terms of, well, we've gone through all the steps. We've worked out what our field is in terms of creation and annihilation operator, which is okay. So I want to come back to the issue of time and how time enters this expression. So I've not put it in anywhere here. It's just a function of x. And the reason why it hasn't appeared yet is because, so I've been working with an analogy with what happens up here, and what we were doing with the simple harmonic oscillator is that we were also assuming that there was no time dependence in these operators. So we're working in what's known as the Schrödinger picture of quantum mechanics, where in the, well, let's define what it is. So above x and this new operator value field that we've just found, phi x, these are in the Schrödinger picture. I'll just write it as SP. Okay, so in the Schrödinger picture, one of the things is that the operators do not depend on time. Okay, so in the normal familiar mechanics that you do, or quantum mechanics that you've done before, you usually you assume you've been taught the Schrödinger picture. So you may not have been specified that it was the Schrödinger picture, but most introductory courses use the Schrödinger picture, and the operators do not depend on time. The thing that does depend on time are the states. States depend on time, the operators do not. So how do the states depend on time? I have a state, let's write psi s. And it depends on time, it's a function of time. I know that this will obey Schrödinger equation. This is the way in which states depend on time in the Schrödinger picture. Okay, but there's different versions of time evolution in quantum mechanics, and in quantum field theory, it can be more useful to use, well, two other pictures. I'm going to discuss one of them now, which is the Heisenberg picture. And then at some point in a few lectures, we'll discuss a third picture, which is known as the Dirac picture or the interaction picture. But today, it's more convenient to work in the Heisenberg picture. Okay, and in the Heisenberg picture, we swap the time dependence around. So in the Heisenberg picture, the operators depend on time, and the states do not. Okay, so there are these two equally valid ways of doing quantum mechanics, and to figure out how to go between them, the most convenient way is to consider the expectation values of an operator, because the expectation value is something that all observers should agree on. Let's imagine it's the expectation value of the position of some particle. Well, everyone should agree what that is. Okay, so let's remind you how to write down expectation values. We want to consider some operator, which I'll call the operator O. Okay, so what happens in the Schrödinger picture? Well, this O has no time dependence. Let me write OS. And as we said above, the states do have time dependence, so my states satisfy the Schrödinger equation. Okay, and there's a special operator, the time evolution operator. Kind of see from just inverting this equation, there's maybe a slightly more formal way to get it, but we'll just jump to the answer where the Schrödinger state at a time t evolves with e to the minus iht times the Schrödinger state at some initial time, just at some reference time 0. Yeah, so this exponential of an operator is going to be defined by the series expansion of the operator. You can just write down the exponential expansion, and that's how you can define this operator. It is a well-defined beast. Okay. So what then is the expectation value? So let's work out what the expectation value is, and in general, it's going to depend on time. In the Schrödinger picture, it's just going to be my Schrödinger state with the operators sandwiched in between, these bras and cats. But I can turn this into an expression that has states that do not evolve with time. So here's an example of a state which doesn't evolve with time. This state is simply fixed to the value it has at some reference time 0. So let me substitute in for the Schrödinger state. Let me substitute in this full expression. So we'll get some time independent state, e to the iht. So we're obviously having to take the complex or Hermitian conjugate of these operators and of the exponential. So this is the expression we have. So now we are free to redefine certain things. Okay, so I said this is a state which no longer depends on time. So this is an example of a state in the Heisenberg picture. Let me rewrite this as psi h, and there's no time label anymore. It's fixed, be the same for all time. I have the Heisenberg state, and then I'm going to define all of this stuff in the middle as the Heisenberg operator. Now it does depend on time, and we have the state psi h again, which is this time independent state. So psi h, this bit, and OH, this chunk of stuff. Have new operator, funny Hamiltonian factors, technically have little hats on everything because they're all operators. And I have a Heisenberg state, time independent. It's just the Schrödinger state at some reference time, so it no longer changes. Okay, that seems fairly trivial. Okay, so far, I hope. What's the point of this, or what can we do with this? Well, one thing we can figure out. We know that these operators should depend on time. So one thing we can figure out is how these things evolve with time. What's the time evolution like? Let's figure out the time evolution of this Heisenberg operator. So we can do that by differentiating our Heisenberg operator with respect to time. So let's find out what the equation of motion is for this Heisenberg operator. So we can do this simply by differentiating this expression with respect to time. Okay, so we differentiate the exponential, pull on a factor of IH. And we go through and differentiate each term one by one. The third one we will pull down a factor of minus IH. And again, if you want to be very rigorous about it, you can just write out this exponential as a series expansion and start to differentiate each term by term. And you'll see that this is indeed what you get whenever you expand the series, do the differentiate, and then resum the series. This is what you will get. Okay, so there's a couple of simplifications we can make. Okay, so let's make some simplifications. The first one is we know by definition these Schrodinger operators do not depend on time. So the time derivative of something that does not depend on time is 0, so this term is going to vanish, this middle term. We know that the Hamiltonian, let's use this color, yeah, the Hamiltonian commutes with itself. So the Hamiltonian also going to commute with e to the minus iht, okay, because as I said, we can use the series expansion, so it'll be 1, the identity operator minus ih plus iht squared over 2 factorial, yada yada yada, the whole expansion. But we're just going to end up with a series of commutators of h with h. Okay, we're always going to find out that we can use the fact that h and h is 0. So in other words, this commutator is 0. So why am I mentioning that? Well, in this last term, it means we can swap the order of h and the exponential term. We're going to use the fact this commutator is 0 to bring the e to the minus iht in front of the lone h. Do that. We get IH, then get this combination e to the IHT OS e to the minus IHT minus I and I'm going to write it as e to the IHT OS e to the minus IHT. Shouldn't use these square brackets. That's what's confusing me, because it makes it look like I'm writing commutators. I'm not writing commutators. I'm just saying here's one term and here's a second term. And here's one term and the second term is the h. So as I said, I'm bringing this e to the minus iht bit in front of the h. But we do end up with something that is indeed a commutator. So it's I, and then we have the commutator of h with this whole bunch of terms. So we have an exponential OS e to the minus iht. But of course, you should recognize that this is just simply the definition of the Heisenberg operator. So this is just the Heisenberg operator in here. So in other words, the time evolution of the operator OH is simply I times the commutator of h with OH. So this is the result we want. This is known as the Heisenberg equation of motion. At least slightly less famous than the Schrodinger equation, but still a very important and useful equation. Okay, so that's Heisenberg operators. Okay, so we've defined what the Heisenberg picture is, what the Schrodinger picture is, and we've now I've now told you how to go between the pictures. So here's how we go between them in terms of the operators, and now we've worked out what the equation of motion is, Heisenberg's equation of motion. The key result is here for an operator OH. Okay, so next I want to turn back to the scalar field problem. Okay, so we've defined this Heisenberg picture, great. We now want to go back to our scalar field operator, and with this machinery of the Heisenberg picture, we're now should be able to calculate what this field operator is as a function of time. So in other words, we're going to go from the Schrodinger picture into the Heisenberg picture. So above, we have this expression that tells us how to go from a Schrodinger operator to a Heisenberg operator. So we basically hit it with these e to the IHT factors. Let's do that. Let's hit with an e to the IHT with our Schrodinger operator that we wrote down earlier. S for Schrodinger, but if I just put the fact that it depends on x and not on t, that will tell you it is a Schrodinger operator. And we can use the expansion that we arrived at earlier of the Schrodinger operator in terms of these creation and annihilation operators. D3A. These are all numbers, so they can be pulled through operators without a problem. And then when we have the raising and lowering operators, we have to be more careful. Lowering operator, we have to make sure we keep the order. Then we had an e to the I a dot x term from our Fourier decomposition. And I think I can fit it in. We have the creation operator term as well. E to the minus ik. Okay, so previously these were operators that didn't depend on time. These were Schrodinger operators, so we can now define Heisenberg, define the Loren operator, Heisenberg operator. So this has an e to the IHT, ak, the minus IHT. And we can use Heisenberg's equation of motion. Here it is for a general operator. We can use this form to figure out how my Heisenberg, in this case, annihilation operator, depends on time, or what the form is. So let's use this Heisenberg equation of motion. We're going to have h in to remind me it's a Heisenberg operator. So this is going to be I times h times the Heisenberg operator. This Heisenberg operator, IH, so we know how to write it in terms of the Schrodinger operator and in terms of the Hamiltonian. So we can expand this commutator out. So it's going to be IH, and we're going to have e to the IHT, ak, e to the minus IHT, minus h. Okay, and then I'm going to use the fact that my Hamiltonian and the exponential of the Hamiltonian can commute to have e to the IHT. We're going to have h, a, k, and I'm also going to use the fact that h and this exponential commute. So I'm going to bring these through so I can, in other words, I'm pulling these exponential factors. So I'm pulling this e to the IHT factor all the way to the left-hand side, and I'm going to pull e to the IHT factor all the way to the right-hand side in both cases. And the bit I'm left with in the middle, well, I'm going to have ak, and then, okay, I'm bringing the h through the exponential, but I can't take it past the ak, so I'm going to have ak h. In other words, I have I e to the IHT, commutator of h with ak, e to the minus IHT. So this is actually a commutator that we know that we know from our study of the simple harmonic oscillator, or at least yes, we're going to assume we know something about it. So let me remind you what we know based on the 1D simple harmonic oscillator. Let me go all the way back. Top. So here we wrote down that h with a in this quantum mechanics example was minus omega a. Okay, so this, in a sense, is a definition of what a Loren operator is. Okay, because it's this commutation relationship that shows you that acting on A reduces the energy by an amount omega. So we're going to take this as a definition in our field theory of what our field theoretic Loren operator should be doing. So later on we could check. So once we've gone a bit further and we get an expression for our Hamiltonian that we'll do soon, you can check that this relation will hold. But at the minute, we're going to kind of take it as an assumption. I guess technically we should do this consistency check. But I think it's also okay to argue that we're doing it because it's the definition of what a Loren operator is. So we're going to use the fact that h k is minus omega k ak. Yeah, I do want to do that. Good. So we can then put that in to our we can then put that into our expression. Okay, sorry, I had to just double check my handwriting, which is always fun. So it's correct, good. So we can put it back in to our Heisenberg equation of motion. So we have I, well, let's take out the minus omega bit. So we get minus I omega k e to the I h t ak e to the minus I h t. Now this bit, remember, is what the Heisenberg definition of the operator is. So we get minus I omega k ak Heisenberg. Okay, so we've arrived at a simple equation of motion then for our Heisenberg annihilation operator. Simple equation that we know how to solve. So of course the solution is that Heisenberg is e to the minus I omega k t with k at some reference value. Where should I put it? Take a bit of space. Operator ak at some reference value as follows. Okay, so again, I can end up with an expression that doesn't involve time dependence of the operator. So I'm going to put all of my time dependence into this exponential factor. So this is going to be nicer to work with. And you can also go through the same argument, or you can maybe also just say it from the fact that the raising operator is the Hermitian conjugate. That we'll get an e to the I omega k t factor times a k0. So I'm going to drop the subscript 0. So when there's no label h on it, as there isn't here, that tells you that it's a time independent operator. Okay, so that means we can substitute back into our field expansion. So here we had a field. This combination is AKH. This is the Heisenberg Loren operator, and we now have an expression for the Heisenberg Loren operator. It has a piece which is time independent, and then we picked up this e to the minus I omega kt factor. Let me bring this expression down by copy it, would be the easiest. We can start to manipulate it again. Let's see. I as a function of x t. I can now replace that Heisenberg quantity because I know how it evolves with time. Put in that it's AK. It's time independent, so I'm going to drop the label at 0. It's just going to be understood to be a time independent operator. And I had e to the minus I omega kt that I need to put in. Comes from this factor. And then I need to remember that I had an e to the I k dot x factor. And I get e ak dagger. I'll get it e to the plus I omega kt, e to the minus I k dot x. I can simplify this a little bit because we know that I'm going to use it k dot x. This 4-vector k dot x is omega at minus k dot x. To arrive at our final form for the field. Now our quantum field, which has been expanded in creation annihilation operators, which is now also a function of time. So we have ak e to the minus I k dot x. This is not a 3-vector, this is a 4-vector combination, plus a dagger e to the I k dot x. So we now have quite a nice compact form for our mode expansion. And it's understood, these guys are Rising and Loren operators in this expression. These are time independent. All time dependence in the e to the plus and minus I k dot x terms. Okay, so let me just recap the key results then. So we've been arguing that this Klein-Gordon equation is an infinite number of simple harmonic oscillators, at least when you look at it in momentum space. The key thing that we introduced, the key recipe we looked at, was this canonical quantization procedure. So it's a 5-step plan you can apply to go from a classical theory to a quantum theory. So we've applied that procedure to the simplest theory that we can write down, which is the theory of the real scalar field. So going through those steps, we've ended up with an expression for the operator valued scalar field. So here it is. So we have phi operator, it's a function of x, it's a function of t, and we write it as an expansion in terms of creation and annihilation operators, where these operators create and annihilate things with a frequency labeled by k, labeled by k. And there's an infinite number of them, so we have to sum over all infinite number of the possible values of k. So that's the end of this lecture.